Hello students, welcome back to another video. Today we're going to be discussing potential and kinetic energy. We're going to learn how to calculate each one, and we're also going to figure out how to manipulate those equations to solve for the other variables within them. Okay, so I'm going to go ahead and start off with kinetic energy. Okay, kinetic energy equals 1/2 mv squared, which is 1/2 the mass times the velocity squared. We discussed this equation last time, but we just did one example with it, and we didn't manipulate it at all. So now I'm going to go ahead and use this equation to do a quick example. So let's say I wanted to calculate the kinetic energy of a race car that has a mass of 1,000 kilograms and a velocity of 50 meters per second. If I were to plug these numbers into their respective places, this is what I would get. Alrighty, so I have 1/2 times 1,000 kilograms times 50 meters per second squared. If I plug that in the calculator, I'll get my answer, 1,250,000 joules. Okay, so that was just a quick example showing how to use that equation in its original form. Now I'm going to show you how to find different variations of that equation to solve for mass and for velocity. Okay, if I wanted to solve for mass, I would have to isolate that variable, which means I need to make it by itself in the equation. So I'd have to move this 1/2 out of the way, and I'd have to move this v squared also out of the way. Okay, to move something out of the way, you need to do the opposite operation of what's happening to it. Here I have 1 divided by 2, so I can do the opposite of that and do multiply by 2 to both sides of the equation to keep it balanced. Okay, that allows me to cancel out the 1/2 and the 2. Then I can get rid of the v squared. Since it's being multiplied, I'm going to divide by v squared. Okay, and then that leaves me with my final equation, 2 times the kinetic energy divided by v squared is equal to the mass. Okay, so there's one variation of that equation. Now I'm going to go ahead and find the equation for velocity. Okay, to solve for velocity, I would need to move the 1/2 out of the way, move the m out of the way, and then get this square out of the way. Okay, so to get rid of the 1/2, I do the same thing as before, multiply by 2. Okay, and then to get the m out of the way, I'm going to divide by it because it's being multiplied. And then the last step is to get rid of the square. The opposite of squaring something is to take the square root. So I'm going to take the square root of both sides of this equation. And the square cancels out with the square root. So now it's a little cluttered, but here I have my final equation. Velocity is equal to the square roots of 2 times the kinetic energy divided by mass. I would be able to solve for velocity if I'm given kinetic energy and mass. Let's say I have an example where I want to know the velocity of a car that has a mass of 1,000 kilograms and kinetic energy of 1 million joules. I would do this. Okay, I would plug this in the calculator. Okay, then I find out that the speed is 44.72 meters per second. So there's another example with that kinetic energy equation, just solving for one of the variables within it. Okay, now I'm going to move on to potential energy. In the video, whenever I was talking about different types of energy, I mentioned that there's 2 different types of potential energy. There's gravitational potential energy, and there's also spring potential energy. Okay, so those are 2 different things that have 2 different equations. I'll start off with gravitational energy first. Okay, so I'm going to notate that with a PE for potential energy and then a little g down here to notate that it's for gravitational. So the gravitational potential energy is equal to the mass times g, which is the acceleration from gravity. And if you don't remember that, it's going to be 9.8 meters per second squared, and then times the height. Okay, so whenever a mass is at a certain height above the ground, the energy is going to be equal to the mass in kilograms times the acceleration from gravity, which is 9.8, times how high it is off the ground. Let's do an example where we have a skateboarder who is going up a ramp, and the height of that ramp is 10 meters, and the mass of that skateboarder is 50 kilograms. Okay, all I have to do there is just plug these numbers in to that equation. Okay, so I have 50 times 9.8 times 10, plug that in my calculator, and I get 4,900 joules. Okay, so that's how you use this equation to solve for potential energy. Now I'm going to show you how to solve for the mass and for the height. Okay, so starting at that same equation, to solve for mass, I need to get the g and the h out of the way. Both of these things are being multiplied, so the opposite of multiplication is division, so I'll divide both these variables to both sides of the equation. This cancels out on this side, and I'm left with just mass is equal to the potential energy divided by the acceleration from gravity, which is 9.8, times the height. Okay, so that's how you solve for mass. If I wanted to solve for height, it would be a very similar process. Okay, to solve for height, I would need to get the m and the g out of the way. So just like I did up here, I'm just going to divide by both those variables. I can cancel that stuff on the right. Then I just have h is equal to the potential energy divided by the mass and the acceleration from gravity. Okay, so that's how you use that equation and put it in different forms to solve for the variables within it. Okay, the last equation I need to talk about is the spring potential energy equation, which looks like this. I'm going to put a little s right there to notate that it's spring energy. Okay, so this one I have some new variables. I have k and an x. The k here is going to be the spring constant. Okay, the spring constant just represents how springy the spring is, how strong is the spring. Some springs are stronger than others, they'll spring out faster and with more force. So the bigger the number, the stronger the spring. And of course the spring constant is going to depend on like what is that spring made out of and how it was made and whatnot. Okay, the x here is going to be the distance that the spring is displaced from its equilibrium position. So I'm going to put displacement. Okay, and if that was a little confusing, I'll explain in a picture. So let's say we have a spring that is in its equilibrium position, like it's not being compressed or it's not being expanded. That's just how it normally is. And let's say I compress it a distance of 1 meter. Okay, so then it turns into this. It's a more tightly wound spring, has a lot of potential energy bundled up in it. Yeah, then in this case the displacement would be 1 meter. Okay, so obviously whenever the spring is not being compressed or expanded, it doesn't have any displacement, so x would be 0. So there wouldn't be any potential energy in that spring, right? It doesn't want to move whenever it's just in equilibrium position. Let's say I want to do an example where I want to solve for potential energy for a spring when k is 0.5 and x is 1. Okay, I would plug my numbers in here. Alright, I plug this in my calculator, or I don't have to for this one. This is 0.5 times 0.5, that's 0.25. And then times 1 squared, this is times 1, so it's just 0.25 joules. Okay, so that's how you would use this equation. Now we can try to solve for the spring constant and for the displacement. Very similarly to how we did it with kinetic energy. Okay, solving this for the spring constant, I would need to move the 1/2 out of the way and the x squared out of the way. So to get rid of the 1/2, just like I did last time, I'm going to multiply by 2 to both sides. I'm going to divide the x squared to both sides because it's being multiplied. I did the opposite thing. And then I'm left with the spring constant is equal to 2 times the potential energy divided by the displacement squared. Okay, and then let's try to solve for the displacement now. Starting with the original equation. Okay, here I would have to get the 1/2 out of the way and the k out of the way and also the squared out of the way. So I would have to multiply by 2. I would have to divide by k, and then I would have to take the square roots of the x squared. Okay, so then I get displacement is equal to the square roots of 2 times the potential energy divided by the spring constant. Okay, I hope this overview helps you guys solve the problems in the Google form and get a better understanding of how you can calculate these energies with those variables. Okay, thank you. Catch you guys next time.